In this section, we're going to talk about limits involving infinity. And another thing is asymptotes of graphs. So look at this graph of a function y equal 1 over x. As you can see that when x approaches to infinity, so that means we're going towards, this direction. When x approaches to infinity, the graph is going down and down and down, meaning the y value is approaching to 0. Similarly, when x approaches to infinity, negative infinity means this way, then y value is again going towards 0. The graph of y equal 1 over x approaches 0 as x approaches to positive infinity or negative infinity. So we say that function has the limit L as x approaches positive infinity or negative infinity. For the positive infinity, we say that L is the limit. That is only possible if this situation holds, which is a very similar definition from previous sections. For every number epsilon positive, there exists a corresponding number m such that for all x in the domain of f, the difference between the f of x and L, the absolute value, is less than epsilon whenever x is greater than m. And the same thing is true for the limit when x goes to negative infinity. So these are the definition we saw in precise definition section of limit. The same thing would be true either we are finding the limit when x approaches to positive infinity or negative. So this is the rules. These are the rules. I took it from the very same limit section section uh, where we define the limit, talk about different properties, sum rule, difference rule, constant multiplication, product rule, quotient rule, power rule, root rule. Just review. In this section, all these previous properties of the limit would also be true either we're finding the limit when x approaches to positive infinity or negative infinity. So the first example here, find the limit of the rational function, this function, when x goes to positive infinity or x goes to negative infinity. So, for finding the limit of this kind of function, try to simplify this function itself. As you can see that if I take x to the power 4 on the top, then factor out x to the power 4 on the bottom, I can see that I can factor out x to the power 4 on the bottom. I can write down 15 over x and then 12 over x squared. So after doing that, I can cancel out this x to the power 4 from the top and from the bottom. So now if I find the limit when x approaches to positive infinity of this function h of x, as you can see that there is no x on the top, and then this expression would go to the 0, and this expression is also go to the 0. Either we take x approach to positive infinity or negative infinity. So when this expression and this expression, both of them are 0, the leftover would be 6 over 8. So the limit when x approaches to positive infinity of this function h of x is 6 over 8. So if we just simplify this, it will be 3 over 4. The same thing is true when x approaches to negative infinity. The same thing happens when x goes to negative infinity. This expression also goes to 0, and this expression also goes to 0. Still, we're going to get 6 over 8, which is 3 over 4 after simplification. So these are the limits when x approaches to positive infinity or negative infinity. Let's see another example. Divide numerator, meaning the top one, and the denominator, meaning the bottom one, by the highest power of x in the denominator. And okay, so here we want to find out the limit when x approaches to negative infinity. For that, we're going to divide the numerator and denominator by the highest power of x on the denominator. That is the that is the hint we have given here. So So look at here on the denominator part, the highest power is x square. And now we can just factor out x square from the bottom one, and from the top one we have to do the same thing. If I factor out x square from the top one, it will give me 1 over x square minus x square on the top one. Similarly on the bottom one, if I factor out x square, it will give me 1 plus 4 over x. So there is a 5. So now we can cancel this x square and this x square. So as x goes to negative infinity, because there is a the power, integer power, it doesn't matter. I can take the this limit inside by using the properties of the limit. We You go back to the this theorem. If there is a power, then I can, number 6 power rule, I can bring this limit thing inside the power. So I'm doing the same thing here. If I take the limit of the things inside this power, then the first term here, 1 over x square, would go to 0. But the second term will be, it will be negative times negative infinity, which is eventually positive infinity. And here on the bottom one, it's 1 plus 4 over x. So 4 over x would go to 0. So it would be eventually 1. So negative infinity to the power 5 is again negative infinity. Sorry, positive infinity. Because this term would be 0 and there will be negative x square. When x approaches to negative infinity, this x square approaches to positive infinity, and there is a negative sign already. That's why that negative. So when x approaches to negative infinity, x square approaches to 0, x square approaches to positive infinity. Because of this minus, it will eventually approach to negative. So one more graph here we can see. This is the graph of y equal 5x squared plus 8x minus 3 over 3x squared plus 2. When x approaches to positive infinity, when x is very very huge, this function, this graph approaches to 5 over 3. Okay, and that you can find out by doing the same thing like we did in this problem. Factor out the common factor from the top. We factor out the highest power of x from the top and highest power of x from the bottom, and we can cancel that, and eventually it will be y equal 5 over 3. So when x approaches to infinity, this function approaches to, graph of this function approaches to 5 over 3, which is actually line 5 over 3. This is the horizontal line. This kind of line has a special name. When x approaches to positive infinity or negative infinity, if the graph of that function approaches to some line, horizontal line, that line is called horizontal asymptote. This line is called horizontal asymptote. So one more graph here. This is the function, and when x approaches to positive infinity, this graph approaches to y equal to 1. And when x approaches to negative infinity, this graph approaches to negative 1. So this y equal to 1 and y equal to negative 1, these are the two asymptotes, horizontal asymptotes for this graph. And now it's a time to formally define horizontal asymptote. A line y equal to b, which is horizontal line, is a horizontal asymptote of the graph of a function y equal f of x if either the limit of the function when x approaches to positive infinity is that value b, or the limit of the function when x approaches to negative infinity is the value b. We go back and look at these two graphs, then it makes sense now, because when x approaches to positive infinity, the graph is approaching to 5 over 3, and then when x approaches to positive infinity, the graph is approaching to 1. That's why y equal to 1 is the horizontal asymptote. Similarly, when x approaches to negative infinity, the graph is approaching to negative 1. That's why this is the horizontal asymptote as well. If we are dealing with finding the horizontal asymptote for rational function, for a rational function, then there are the three things we can check. First of all, a rational function means there will be a polynomial on the top, on the numerator, and then polynomial on the denominator. If the degree of the numerator is less than the degree of the denominator, meaning the top one, the degree of the top one polynomial is less than the degree of the denominator, then the horizontal asymptote would be a y equal to 0. If the degree of the numerator, that means the top one, is greater than the degree of the denominator by just by 1, then no horizontal asymptote is possible. The only thing we can find in this case is slant asymptote. Slant asymptote, the horizontal asymptote means, this horizontal line. Vertical asymptote means vertical line. Slant means it's neither horizontal nor vertical. Okay. So when the degree on the top is 1 greater than the degree on the bottom, then we can find out the slant asymptote. And we're going to do one example where we will see how to find the slant asymptote. Finally, the degree of the numerator is equal to the degree of the denominator. In that case, horizontal asymptote can be found by writing y equal the leading coefficient on the top over the leading coefficient on the bottom. If a is the leading coefficient on the top of the polynomial and b is the leading coefficient on the bottom of the polynomial, then for the equal degree rational function, the equal degrees on the top and bottom, y equal to a over b would be horizontal asymptote. One example here, this is a rational function. As you can see that the degree on the top is 4, the degree on the bottom is 4. So in this case, this third property will help us. In this case, y equal coefficient of highest degree term on the top is 4, the coefficient of highest degree term on the bottom is 5. So y equal to 5 is horizontal asymptote. Horizontal asymptote. So now we're going to define uh, the infinite limit. We say that the function approaches infinity as x approaches some constant value, and we write this: the limit of the function when x approaches to c is infinity, and this is the proper way to define. This is the proper way to write it down. Similarly, the limit would be negative infinity, and this is the proper way to write it down. So one example, as you can see that when x approaches to, as you can see this graph, when x approaches to 0, when x approaches to 0 from the right side or from the left side, the graph is approaching towards positive infinity or negative infinity. So in this case, when x approaches to 0 from right side, the graph of the function, as you can see, approaching towards positive infinity. Similarly, when x approaches to 0 from the left side, the graph is approaching to the negative infinity. This is called infinite limit. And then whenever this situation happens, this vertical line x approaches to 0, so this vertical line x equal to 0 is called vertical asymptote. So this is the proper way to define the vertical asymptote. A line x equal to a is a vertical asymptote of the graph of a function y equal f of x if either, when we try to find out the limit of the function from the right side or left side, if the limit is either positive infinity or negative infinity, then x equal to a is a vertical asymptote. So in this graph, as you can see that this is the function, rational function, and when we divide x plus 3 by x plus 2, it will give us 1 plus 1 over x plus 2. And when, as you can see this graph, when x approaches to negative 2 from left side, from this side, when x approaches to negative 2, the graph is approaching to the positive infinity. And when x approaches to the negative 2 from right side, the graph is approaching to the negative. So that means this x equal to negative 2 line is our vertical asymptote. So same thing goes here. The function is negative 8 over x squared minus 4. So anything which makes this denominator 0 gives us either positive infinity or negative infinity for these functions. That's how we find the vertical asymptote. For finding the vertical asymptote, just make denominator equal 0 and solve for x. So as you can see that when x is positive 2, which is this one, this line, and when x is negative 2, the graph is approaching towards positive infinity. So when x approaches to positive 2 from the left side, it's approaching to the positive infinity. From the right side, it's approaching to the negative. When x approaches to negative 2 from the right side, the graph is approaching to the positive infinity. From the left side, it's approaching to the negative. So that means x equal to positive 2 and x equal to negative 2 are two asymptotes for this graph. Sometime we might have to find you know the limit of this function. When x approaches to 1, what happens to this function? If we try to plot the graph of this function, let's say this is x equal to 1, the graph of this function would look like this. This is x equal to 1. When x approaches to 1 from right side, from this direction, when you are going towards 1, the graph is going towards negative. Similarly, when x approaches to positive 1 from left side, again the graph is going to the negative. So that means the limit of this function would, and as you can see that this x equal to 1 would be vertical asymptote. Vertical asymptote. You don't have to mention about this, but that's how you find the vertical asymptote. So in this case, in this problem, we need to find out horizontal, vertical, and oblique asymptote whenever it's possible. So if you, for the horizontal asymptote, if you go back and check this rule, whenever the degree on the top is 1 degree greater than the degree on the bottom, then the slant asymptote is possible. No horizontal asymptote. So in this case, the degree on the top is 1 greater than the degree on the bottom. So whenever you have this kind of situation, to find out slant or oblique or slant, that means the same thing. Find out the slant asymptote or oblique asymptote. You just divide the numerator by denominator. If I do that, I'm going to get um, 77x positive, change the sign, 530. As you can see that whenever you have the function, rational function like this, where the degree on the top is 1 greater than the degree on the bottom, we can divide the top one by the bottom one, and we can rewrite this as 11x minus 77 plus uh, uh, that negative 539 over x minus 7. So when x goes to 7, this part, when x goes to 7, this part goes to infinity, right? So that's why the vertical asymptote is x equal to 7, and then oblique asymptote is this part, y equal 11x minus 77. This is slant asymptote or oblique asymptote. X equals 7, which makes the denominator 0, is the vertical asymptote. So there is no horizontal asymptote for this. So that's section. That's this section where we found at in or infinite limit